Organized by IEEE ComSoc WTC Special Interest Group of RSMA. So this is the first webinar this year, and it's our great honor today to have Professor Zilong Liu from University of Essex as our distinguished guest speaker. So please allow me to make a brief introduction of Professor Liu. Professor Liu is now an associate professor and the 6G lab manager with the School of Computer Science and Electronic Engineering, University of Essex. His research generally lies in the interplay of coding, signal processing, and communications, with a major objective of bridging theory and practice. His recent research interests include advanced 6G V2X communication, sensing, and localization technologies for future connected autonomous vehicles, as well as machine learning for enhanced communications and networking. Prior to his current position, he was with Hangzhou University of Science and Technology, Tsinghua University, Nanyang Technological University Singapore, University of Melbourne, the Hong Kong University of Science and Technology, and the University of Surrey. So details of his research can be found at his personal webpage. And before the talk, I would like to remind the rules of our webinar. So during the 15-minute talk, please keep yourself muted and you can type your question in the chat box. After the talk, we will have an around 10-minute Q&A session, and you can unmute yourself to raise your questions, or I will choose 2 to 5 questions from the chat box. Okay, so now enjoy the talk. Let me stop sharing.
Thank you, Nina. Thank you so much.
Okay, Professor Liu, you can share your screen now.
Yeah, let me share my screen from my side.
Okay.
Continue to share, yeah? Okay. Can you see my screen?
Yeah, perfect.
Okay, good. Let me set a timer. So I try to finish my talk within 45 minutes. So I set a timer in my site. Thank you, everyone, for coming to my talk. It's my honor, and thanks so much for the invitation. It is a promotion to me. So the talk today is on the codomain normal for 6G. Before I start, I would like to thank the generous funding support from the following 5 projects. Basically, I started my research when I first moved to the UK in January 2018. During this EPSC project, I worked with Professor Pei Xiao, and then later on, we jointly supervised Dr. Chulo. And so from that project, we started to formally look into this the research on the codomain normal. And then since I moved to the Essex, we carry on this research. And now you can see the last 4 projects, especially for the 5th project with jointly with into Singapore. So I worked with my PhD supervisor, Professor Yunliang Guan, and so we developed a demo, for this research, and I will show such a demo later. This research is divided in. This talk is divided into 7 sections. I will first talk about the background of this research. I will introduce the power imbalance codebook design, and I will compare the SMA with the power domain normal, and I will compare SMA with dense code multiple access DCMA. And I will introduce some of our research on the integration of the OTFS and the SMA for high mobility channel. And I will also show some demo, based on OFDM SMA. Finally, I will conclude and this talk, and I will show some future direction. So 6G is coming, and so from the 5G to 6G, we are further pushing the limits of a number of KPI. So in this figure, now we can see that we will need to further push the spectrum efficiency in terms of mobility, latency, and collection density. So in particular, in terms of the collection density, in terms of the number of devices per kilometer square, now we can see that this target has been raised from 10 to the power 6 to 10 to the power 7. So basically, this means that within 1 meter square, yeah. So we need to support 10 devices, uh, in terms of the communication. So we can imagine, the room that we have now, how many square meter, yeah, and then in terms of our campus, how many square meter. So really, for us to meet such a target, high collection density, we need to have some very innovative approaches. In the past few years, numerous research have looked into now so-called multiple access called LoMa. So LoMa, basically, we have two types of LoMa. One, the type 1 is called the power domain LoMa. So basically, the idea here is that, we have two user, and we separated out these two user in the power domain, whereas we are sending them over the same and time and frequency resources. So such a power domain NORMA, in terms of its idea, is very simple. But in terms of its implementation, it's not so simple. First of all, for us to really find out the two user, and then that we need to carry out some very complicated and closed loop power control, such that we are able to properly configure the power to this two user. And so in this case, since the one user will always get a higher transmitted power, and then the other user get less amount of power. So in this case, it's very hard for us to maintain the fairness of the communication. So this is number one. Number two is that, for us to carry out this decoding, so we will need to first decode out, the signal from the strong user, and then followed by SIC. But however, it's not easy to guarantee that, we're going to have the perfect SIC. Not to mention, in terms of the scalability, flexibility. So from industry point of view, over the past decade, industry basically very much favors the codomain NORMA. So the codomain NORMA, in fact, it evolves from the traditional CDMA system, where we have a number of users, where every user is giving a sequence or a code. So by carefully designing, those spreading sequences, such that they're able to have some very good autocorrelation and cross correlation, and then at the receiver, we are able to separate them out through the match filter multi-user detection. So starting from this CDMA, so in the 5G time, there are numerous proposals talking about the codomain NORMA. Now we can see many types of codomain NORMA, such as IDMA, where we have used the different interleaver for different user, and this such that we're able to separate different to carry out the multi-user communication, such as MuSA, PDMA. So overall, so there are many proposals. In 5G time, actually, 3GPP has received numerous proposals on codomain norma. So, for example, we have a SMA from Huawei, we have a PDMA from a CAT, and we have a MuSA from ZTE, we have a NCMA from LG. So eventually, since they have a numerous proposal, and then it's not easy to achieve that consensus. So eventually, although previously we saw, it is very likely for a widely regularized codomain norma to be written into the 5G new radio, but so far we don't see it happen. So our vision is that moving towards the 6G, we believe that codomain norma will be a must, and it is also likely for the codomain norma to be integrated with risk splitting multiple access towards a universal multiple access. And I will talk about this in a later slide. So first of all, let me introduce the original idea of the SMA. So it is called the low density signature, the CDMA. Such a paper was published in 2008. So now we can see the transmitter here. Basically, it is essentially the same CDMA transmitter where every user will carry out the symbol modulation and then followed by spreading. Okay, so in this case, from the receiver point of view, we will see the system equation y equals to hx plus w, where h refers to the effective channel matrix. So in this case, if we carry out the ML decoding, so in this case, we have the complexity of m to the power j, where m refers to the modulation order and j refers to number of user. So of course, when the number of user is very large, and in this case, we are unable to afford the ML detection. So what we can do is instead of using some dense sequences, all right, so here we can actually consider some sparse sequences. So here now we can see that we have a 16 user, where every user is giving a colon vector, which will be served as a spreading sequence. So whenever this colon is 1, so this means that we'll be using non-zero element for spreading. And whenever it is 0, so this means that we're sending a 0 loud signal out. Okay, so in this case, thanks to such a sparsity, we are able to leverage some sort of believed propagation decoding, and then we're able to relate such a system, to a factor graph. So if you are familiar with the coding theory, particularly for the decoding of LDPC code, and then we know that we're able to use the BP for some very efficient decoding. So in this case, we're able to reduce the decoding complexity from m to the power j to m power of dc, where dc refers to number of users superimposed in each resource load. So in this case, we have the dc equal to 4. So meaning that we have in this resource load, we have a 4 user superimposed over one subcarrier, for example. Okay, so based on that, Huawei noticed such a technique, and in 2013, they published a conference paper. Later on, they got their patent, and so they further developed into the so-called sparse code multiple access, and we can regard this as a generalized low density signature. So basically, what we can do is that if we look into the frequency domain, so we are able to, so basically we can divide the frequency domain into several blocks where every block has a 4 subcarrier. So in this case, if we use the conventional OMA to do the transmission, now we can see that maximally we're able to support the 4 users, right? But now, by using SMA, we're able to support 6 users. So in this case, we can increase the overloading from 100% to 150. So the key point here is to develop some code books. So basically, we have 6 layers here, and we need to have 6 code books here. And so basically, whenever the layer 1 wants to send out the base 11, and then we select the last code word from such a code book. And similarly, let's say for layer 5, whenever we want to send 01, and then we send out the second code word, from its relevant code book. Okay, so on and so forth. And then so now you can see, by looking to this code book, and then SMA also maintains the sparsity. Therefore, we're able to use the massive parsing to carry out this decoding. So now the next question is how we are able to design such a SMA codebooks. So so for that one, I would say, this our design is very different from the design of risk splitting multiple access. So we mainly look into the pairwise error probability (PEP). So if we assume that the vector X is sent out from the transmitter, and then because of the noise and multi-user interference, so the receiver thinks that vector Y is received. So according to this TIT paper, we're able to upper bound such a PEP, in such a way. So by looking into this equation, now we can see that, for us to minimize this PEP, so we simply need to minimize this upper bound, okay? Now it turns out that, we just need to maximize the minimal product distance, which is shown here, if our channel is a relay fitting channel, okay? But once we have a Gaussian channel, so in this case, we can prove that, we simply need to maximize the minimal Euclidean distance, all right? So, this is one of the major design criteria. Besides that, we also wish to maximize the diversity order. So basically, by looking to this BR curve, okay? So basically, a larger diversity order means a sharper BR curve here. So basically here we can see this green curve will enjoy a larger diversity order because we're going to have a much better BR with an increase of EB anode. And so later on we will come back to this the diversity order, okay? And then of course, through this proper codebook design, we're able to enjoy certain coding gain. Basically, we're able to move this blue BR curve to the left, and then now we can see that from this blue curve to this red curve, we're able to enjoy certain coding gain. Okay, so and of course, we also wish to minimize this Kissing number, and so for both this relay fitting and the Gaussian channel. So based on that, I would like to introduce some of our work on the power imbalance codebook design. And it all started from this conference paper in 2019. So our idea is that instead of having uniform power allocation for all the user, so we kind of consider to have certain non-uniform power allocation among the different users. So if you look into this spreading matrix where every column is used as a sparse sequence, now we can see the sequence energy, will change from here to here to here to here to here. All right. So by looking into the bit error rate, now we can see that in terms of the relay feeding channel, our proposed design is able to achieve a comparable BER as that of the conventional one. However, in terms of the Gaussian channel, we are able to achieve the best bit error rate. So starting from this research, we look into this power imbalance SMA codebook design in 2022, and we published this paper in TVT. And then so our key idea is to allocate different power level to a different user, such that we are able to purposely amplify the near-field effect. So, and then we found out that by doing so, it is actually likely for us to achieve a larger minimum Euclidean distance, and then hence we're able to have the better interference cancellation. Here now you can see the example of our design codebook, and you can see our power allocation among different users. So in this case, for the 4x6 SMA system, now we can see that by using our proposed codebook, we are able to achieve the largest minimum Euclidean distance, and we're able to achieve a very good minimum product distance. So in this case, now you can see that our codebook is able to enjoy the best bit error rate in the Gaussian channel. And for the 5x10 SMA system, now you can also see our BR performance. So it if you look into this red curve, this actually refers to the BR of our proposed codebook. And in later on, we generalize such an idea, and then we look into the power imbalanced DSMA codebook design. We consider the Lagami channel characterized by an important parameter M. So basically, when M equals to 1, we have the relay feeding channel. When M is an infinite number, so then we have the Gaussian channel. And so it turns out that we just need to maximize this matrix, okay? And importantly, we can actually prove that when M is equal to sufficiently small, and then such a matrix would reduce to the minimum product distance. And similarly, when M is sufficiently large, and then we're going to have the minimum Euclidean distance. So we proposed the effective method to optimize it. And now you can see our optimized power allocation among the different users. So here is for 4x6 system. Here is a 5x10 system. So now you can see our performance. So here is our proposed codebooks, and in terms of the minimum Euclidean distance, we're able to achieve 1.24 compared to the SMA system. And similarly, once we have the overloading of 200%, and then we're able to achieve the minimum MED of 1 compared to SMA, where the maximum MED is 0.63. And this can be reflected in our bit error rate performance. Now you can see our bit error rate performance of DSMA, where we can always achieve the lowest bit error rate compared to SMA. Now, I want to move to the comparison between SMA and the power domain normal. Basically, our idea is that, we really wish to see that if we don't, even we don't talk about the flexibility, scalability, but we simply talk about the beta error rate and then how much gain that we are able to achieve between SMA and the power domain normal. So in this case, we consider we consider 2 times 4 power domain normal. So meaning that we have a 4 user, they are sharing 2 subcarrier. So in this case, we are going to have a 200% overloading factor. So in this case, we consider this a 5 times 10 sparse matrix where every user is giving 5 subcarrier, all right? However, among these 5 subcarrier, we only send out our signal over 2 subcarrier. So in this case, now we can see that both systems will have the same diversity order of 2. Okay, so it is a fair comparison. Okay, so now you can see the power domain normal performance using SIC. Okay, now we can see that performance actually is pretty bad. But even we use the generous sphere decoder, you may simply regard this as a ML receiver. Now we can see that still using SMA, we're able to achieve about 3 dB gain. And furthermore, we consider the coded bit error rate comparison. We use the 5G new radio LDPC with a rate that we can see here. Now we can see that under the uplink relay feeding channel, now we can see that using SMA under the massive passing, the decoding, we're able to achieve a huge gain compared to the power domain normal. So here is this. So our message is that really by so since in SMA we're able to carry out this proper codebook design, and then we're able to have some very good constellation shaping gain, and then we are able to enjoy a kind of signal diversity. This actually explains why we are able to have such a performance gain. So now I would like to move to the comparison between SMA and DSMA. So now if we look into this factor graph, which shows a 4 times 6 SMA system, basically we have 4 subcarrier and we have a 6 user. All right. So by looking into this factor graph, now we can see that every user is sending a signal over 2 subcarrier. All right. So in this case, now we can actually prove that every user will have the diversity order of 2. So as I mentioned in the beginning, to achieve a large diversity order is very important for us to further reduce our beta error rate. All right. So now the question here is that how we're able to achieve a larger diversity order for SMA. So then you may think that okay, so it's actually very simple. Instead of sending each user signal over 2 subcarrier, now we can send each user signal over the entire 4 subcarrier. But in this case, now you can see that we are losing the codebook sparsity. Okay, so then we are unable to use the massive passing to carry this decoding, but also it's likely for us to enjoy a higher diversity order. All right, so this actually explains the main problem of SMA, which suffer from the limited diversity order. So now the next question is if we kind of move from this SMA to kind of dense code multiple access, okay? Because once we send every user over the full subcarrier, then we are going to have the DCMA. So what will be the performance gap? So now I want to show you our design. So in this paper, we have carried out a comparative study of codomain norma in terms of using sparse codebook or dense codebooks. And we consider, some special DCMA codebooks from the transpose Vandermonde matrix. So our target here is to maximize the minimum product distance. And we have referred to some nice Vandermonde matrix in this two paper. And so our idea is to first generate such a Vandermonde squared matrix, and then we can kind of randomly select a few rows, from such a squared matrix, and then based on that, we kind of to have one spreading sequence for layer 1 and then one spreading sequence for the layer 2. So moving on, now the next question is how we're able to decode such a system. So for that, we have used the generous sphere decoder for such a rank deficient DCMA system. And so in this figure, we have compared the complexity between DCMA and SMA. So in terms of the 4 times 6 normal setting, now we can see that DCMA is actually enjoy the lowest complexity. But once we move to the 5 times 10, now we can see that DCMA enjoy a slightly higher complexity. But overall, for the small scale normal setting, the SMA and DCMA may have a relatively comparable complexity. However, we also observed that, once we move from a small scale to a large scale, then, it may become very hard for us to use the generalized sphere decoder to carry this decoding. And so that's in terms of the complexity. Now, in terms of the beta error rate, all right, so here we have compared this beta error rate for 4 times 6 codomain normal system in the downlink channel and the 5 times 10 codomain normal system in uplink channel. So in this case, now we can see that really this DCMA is able to enjoy a much steeper BR slope, meaning that we are able to enjoy the full diversity order. And then this from here now we can see that DCMA is able to achieve a much better beta error rate performance compared to SMA. So next, I'm going to introduce you the integration of OTFS and the SMA. So conventionally, we implement the SMA through OFDM system. So the system is effective for the quasi-static channel. But however, once we consider some high mobility channel with a large Doppler or large CFO, and then now in this paper we can see that even we have the normalized CFO of 4% of the subcarrier spacing, now we're going to have the beta error rate floor. So this means that if we use the OFDM to support the SMA, we may not be able to achieve a very good BR performance, in high mobility channel. So this actually motivated us to look into OTFS modulation. So essentially, the OTFS modulation is about a kind of a two-dimensional transmission starting from delay and Doppler domain from here. And we send out each symbol in the delay and Doppler domain. And then, so such a symbol will be converted to the time and the frequency domain, which is equivalent to a kind of spreading. So because of such kind of spreading in the time and frequency domain, and then we are able to achieve a much higher diversity order compared to conventional OFDM system. So in this paper, my collaborator, Dr. Kunta Dika, they look into integration of OTFS and SMA. So their idea is that they first do the SMA encoding, and then they put the different SMA code words in the delay and Doppler domain, and then followed by OTFS modulation. So in the receiver side, they consider a two-stage detector. So they first carry out this OTFS demodulation, followed by linear MMSE detector, and then which is equivalent to the equalizer, and then finally they carry out the SMA detection. So we were motivated by such a paper about we look into a new kind of massive parsing called the OMP. Yeah, so we don't have time to go into the detail of the OMP, but the major message is that by using the OMP, we're able to achieve a better iterative decoding performance as because we are able to converge to a globally optimal solution. Okay, so and then so here is our system structure for our proposed OMP-aided the cross-domain OTFS SMA receiver, and so at the same time, we consider the vehicular scenario where many cars, they are driving in the same direction. So in this case, if we group several vehicle, using one SMA transmission, so we believe that they are able to talk through the D2D communication. So in this case, they are able to share their decoding message. But then at the same time, since they are driving in the same direction, and then they are driving in almost the same moving speed, so their the Doppler, between them might be very small. So in this case, we consider the single layer receiver where each user carries out independent decoding, and we also consider the multi-layered receiver where each user carries out their decoding, and then at the same time, each user will share its decoding message to the surrounding vehicle. So in this case, we can see our BR performance. And here we consider the carrier frequency is at 4 giga, and the subcarrier spacing is at 15K. And we consider the maximum user speed is 500 kilometer per hour. And now you can see our PDP, the power delay profile here. So compared to this two-stage detector, now we can see that by using our cross-domain detector, now we're able to achieve a much better BR performance. So L equals to the iteration number. So when L equals to 5, now we can see that beta error rate starts to converge. And so more clearly, now we have plotted out, the mean square error versus the iteration number. So now we can, using such a curve, we're able to analyze, the maximum number of iteration we need to carry out in such a receiver. And so furthermore, we have compared our beta error rate, in terms of the single layer cross-domain receiver, and then we compare this with a single user beta error rate, which is shown here. And actually, it is very interesting to see, once every user, starts to share some of their message, to its surrounding vehicle, at 20%, we're able to achieve the BR of the single user one. And so the more that we can share, now we're able to further push this BR to the left. So here now you can see that BR with 80% of sharing. Now you can see the further, here is with a 50% sharing, now with 80% of the sharing. Okay, so this is on integration of OTFS and SMA. So finally, I want to talk about a little bit on our demo design. We consider a frequency hopping system to avoid, some subcarrier maybe, some user may be stuck to some deep feeding, okay? And so for the lab environment demonstration, we kind of group 3 users into one transmitter, and then we group the other 3 users into another transmitter. And we consider the 5G new radio LDPC with a rate of half, and we consider SMA equilibrium over with m equal to 4, and we consider the cyclic frequency hopping pattern, and we consider the 802.11p OFDM structure with 64 subcarrier, and then among which we have inserted several pioneers, and then eventually we have used the 48 subcarrier for data transmission. And now you can see our system structure. One is this structure for picture transmission, and then the second one is for the video transmission. So now you can see the transmitter, so the transmitter is here, and then we kind of have 2 transmitter, send out from the same, 2 transmit antenna send out from the same USRP board. So here, for the lab environment, we want to make it controllable such that we're able to control the inter-user delay. Because for uplink, once we have some inter-user delay, in this case, it might be very hard for us to compensate it in the receiver side end. So now let me play my video. As I hope I'm in time, right in time. Okay, good. So the first video is on the picture transmission. Now I'm going to play. So now you can see our transmitter. Here is our transmitter. Oh no, here is our transmitter setting, and we consider we have used the carrier frequency of 5.4, and we have used the FFT size of 124. And so here now you can see we have a 2 transmit antenna where 3 users are sent out from 1 antenna, and then the rest 3 users are sent out from the second antenna. Now you can see our receiver on. Now you can see that we can see the 6 picture, sent out from this 6 user. Now you can see change of this picture. Now we are using a jar here to block the transmission of 1 transmit antenna. Now you can see the poor receiving performance of 1 user picture, and then finally you can see that we can see the decoding failure of the user 5 and the user 6. But once we remove this jar, and then now we can see our performance will return to normal. Okay, so this is for the first demo. In the second demo, so I'm going to show you. So I will need to move to the next one. In the next demos, I'm going to show you the video transmission where we have a we have a two transmitter to emulate the uplink transmission where three users are grouped in one transmitter, and then the remaining three users are grouped into the second transmitter. And then, so since it is a video transmission, so it is actually pretty challenging. So I can show you this video now. So here is our transmitter side. Now you can see the baseband spectrum. Now you can see all the cable collection. We have a Usenet external clock to synchronize, the clock of these two USRP. Now we can move to this receiver end. And now you can see our spectrum, based on this spectrum analyzer. And now we can see a smooth transmission of this two video. And so basically every video has the data rate of 600 and using the carrier frequency of 5.9. So here is this demo. All right, so now I think I will move to the final. Okay, now let me move to the conclusion, the future work. So in conclusion, I have argued that we believe that codomain normal is a must for 6G, because in 5G we don't see any normal scaling rating into the 5G standard. And in this talk, I have introduced you about the codomain normal codebook design. I have introduced you the power imbalance codebook design, and I have shown you that the power imbalance is actually very useful for enhancing the codebook distance in terms of the minimal Euclidean distance or the minimal product distance. So the key idea here is to purposely amplify the near-far effect. And here I have compared the SMA with the power domain normal, and we have shown that SMA enjoy a large coding gain. Not to mention is flexibility and scalability. And in terms of the diversity order, and we have shown that DCMA can be designed to enjoy the full diversity order. And so this can be reflected to the BR or the DCMA. And then in comparison, SMA suffer from limited diversity order. And in terms of the comparison, we have shown that, for the small scale DCMA system, for the small scale normal setting, these two systems have a comparable complexity. And in terms of the PPR, we have some results to show that DCMA enjoy a lower PPR. And finally, we have some future work. Number one, we believe that it is very important for us to develop some tool to analyze the convergence for the different codomain normal system, in terms of long packet and short packet transmission. And secondly, how can we optimally match a channel code to a codomain normal system. And then so for that, we believe that such a convergence analysis might be useful. So thirdly, we have carried out some research, in terms of the integration of SMA with AFDM, SMA with OTFS, but the general integration of a codomain normal with this different waveform is still missing. And we also believe that, we can use some deep learning or some other AI machine learning approach, to carry out the code design and even detection. Finally, we believe that it is actually timely for us to consider a unifying framework, which is able to unify all the possible multiple access. So, in particular, in the paper below by Professor Brolo and Professor Yijian Mao in Shanghai Tech, they have actually mentioned that this UMA should further shrink the knowledge tree of MA scheme by unifying the RSMA with all other dimensions, such as codomain multiple access, and ultimately provide a unified and conceptually simple understanding of the current and future models of multiple access scheme. Such UMA does not exist yet. So, one major idea is that, based on this SMA structure, so it is actually likely for us to use one layer to send out the common message, and then we can use some other layer to send out some private message. But a careful analysis, deeper analysis for this arrangement is still missing. So finally, we have some selected publication, on application of codomain norma. So in particular, in this paper, we have shared some preliminary result online, in terms of risk splitting SMA. We have submitted such a paper but got rejected. So we are revising such a paper now. And we, in this two paper, besides the integration of OTFS, so I have worked with my collaborator in University of Surrey, Dr. Chulo and Professor Pei Xiao. We have done the integration of AFDM and SMA. And regarding the codable design and the system analysis, we have done many results here. If you are interested, you are most welcome to look into this paper. I think I have come to the end of this talk. Thank you very much.
Thank you. Thank you, Professor Liu, for the very interesting talk and the very rich references for us to learn the codomain norma. All right, so any questions from our audience? If you want to raise questions, you can, of course, unmute yourself to raise the question, because I see there's no question in the chat box.
Alternatively, yeah, so alternatively, you can type down your question in the chat box, and then we can see it.
Yeah, the audience may be a little bit shy, so maybe I can start with the questions first.
Yeah.
Actually, for the last slide, I'm very interested, as you already mentioned that you already done some combination between these codomain multiple access together with ray splitting. So would you mind make some brief insights to show how RSMA can be combined with this codomain, and what can RSMA do in this combination? I mean, is it still utilize this message splitting to do interference management, or it can be used to with other function?
Yeah, so I believe that we have a lot of things to do. Number one, if you look into the current RSMA literature, so basically we are using a top-down approach that we first analyze, the summary or the entire system troop, or in terms of the system capacity, and then we mainly look into the from the capacity rate point of view, and then we do some analysis, right? But in terms of the SMA, we directly look into the bit error rate. Okay, so what we believe that from the application point of view, it would be really nice for us to see how RSMA can perform in terms of its bit error rate. So here we can see some very unique linkage here that by let's say for this 4x6 SMA structure, if we're able to use a 1 layer or even 2 layer to send our comment message, and then how we are able to see some new insights out. And I can see that, for us to carry out this kind of message splitting, we will need to consider the unique structure of the SMA to carry out the rate analysis, and then such that we're able to match specific, the modulation order as well as the channel code. So overall, I can see, such a direction is still missing. Yeah, so I would highly encourage us to look into it. And in this paper, we have some shared some preliminary results online. If you are interested, you can simply type rate splitting sparse code multiple access. But here, we are still trying to do more and then to meet the requirement of our reviewer. Yeah, thanks a lot.
Thank you, Professor Liu. I think Sibo has also a question.
Go on,
Yeah,
please.
Sibo,
Yes, go. Yeah.
you can unmute yourself. Yeah.
Yes, thank you, Professor, for your great presentation. I actually have been aware of your research for a while, and plus I'm doing rate splitting. I've thought about combining rate splitting with SCMA, and also well, before I thought about it, and I know that if I want to do it, I would follow the figure you have here, having the common stream as CMA coded and transmitted with all other streams. And I also had the honor to read your paper on rate splitting SCMA. But I think in that paper, the common stream was not SCMA encoded. It was just transmitted through all the resource elements and then applying a successive interference cancellation as a receiver. And I remember that there was a remark in that paper saying that if the common stream is transmitted through a CMA, there will be higher complexity at the decoder. Could you comment a bit on that?
Yeah, so basically, this research was carried out with my collaborator, Minawa, who is online now. So our idea here is actually the main challenge here is how to match that kind of common message right into here, because once we have this channel coding, and then so the challenge here is how we can group certain common message from the different users, such that after this channel coding, and then we are able to have the same number of message bits as that for the private message. So we look into that, and we found out that it is not so easy to find some very specific channel coding with that kind of specific rate, which is help. I mean, which can help to do so. So then in the paper by Minawa, so we actually consider different types of comment message sending that we still consider this 6 private message, but then what we do is that we superimpose the common message over the 4 subcarrier, that then we can use some QPSK or BPSK to send the common message. But I think for that paper, one issue for that is that since we are not following this kind of top-down approach, so we feel it is not so easy for us to convince people who are doing the research on RSMA. Basically, we are following the bottom-up approach. So yeah, now we are still improving such a paper. So I hope that I can share with you such a paper, once revised version is ready. Yeah, thanks so much, Sibo. Yeah, so I hope
Thank you.
I have
Thank you.
give you some insights. Yeah.
Yeah, thank you. And I look forward to reading your future work.
Yeah, thank you, Sibo. Thank you.
We still have a question in the chat box saying, Professor Liu, may I ask if aperiodic frequency hopping sequences can be applied to code domain normal?
What is the question? Sorry, can I see? Hold on. Probably I will. All right. Aperiodic frequency hopping sequence can be applied. Yeah, certainly. So I believe. So I mean, essentially, we can regard this codomain normal as a generalized CDMA, I would say. All right. So I mean, in the past, CDMA has achieved a huge success, but later on, because of this patent problem of Qualcomm, CDMA was stopped in 4G. But now, I think in 5G time, 6G time, I would say that the golden time of the sequence is yet to come, and then we are able to use some very good aperiodic frequency hopping sequences for code normal. And actually, besides my current research on code normal, previously we have many publication on sequences. Yeah, so I would be very happy to talk to you, if you are interested in some lines hopping sequences. Yeah, thanks.
Thank you, Professor Liu. So I have one last question about your implementation, because you already implemented this OFDM SCMA. I'm curious whether, because in your discussion on this OTFS SCMA, you're also showing the figure of these VTC applications. I'm wondering whether you have already implemented this OTFS SCMA in your trail, or
Good question. But yeah, so we do have a plan now, but we have some challenging situation because once we want to showcase, the strengths of OTFS, then in this case, probably we'll need to drive a car on the road and then demonstrate it. So for us, we have very limited resources. So now we can see that we only show that in the lab environment. So this actually, but here, even in such a setting, so we try to demonstrate out, here it is the uplink OFDM SMA transmission. And so even for the picture transmission, we have aligned these two transmit antenna in the time domain, and then we want to control the timing. But in this case, we haven't done so, but we can achieve a very smooth video transmission. But I know, into Singapore, they are doing some trial work, in terms of the OTFS. According to them, their plan is that, eventually they will need to drive a car which carries the receiver. and then they have a transmitter on the roadside unit, and then they will see how such a system will perform. But in the UK, we feel we have very limited resources, and then we was and probably we will try some simpler way, to demonstrate out. Yeah, so we will definitely we will try to do so. Thank you.
Yeah, it's very interesting because I am wondering whether this high mobility can actually show its performance gain in this trail, because I think it
Yes.
will be very appealing, especially in V2X applications.
Yes, indeed. So from the application point of view, I think it's not just the V2X that we can use the OTFS and the SMA, but we can also consider the satellite
Yeah.
IoT
Low
point
Earth
of
orbit.
view. Yeah, let's say we have the Liu satellite, and then let's say we have a fleet of new satellites, and then we want to use them to serve many sensors on the ground. So in this case, we need to face the same issue of the high Doppler. So, and then of course, it would be very useful for us to consider the integration of SMA with OTFS, and the integration of SMA with AFDM. Yeah, so you are most welcome to look into our research paper here. Thank you.
Thank you, Professor Liu. All right, so if there is no other question, I will end the webinar today. And let's thank Professor Liu again for the very insightful talk, and thank you all for attending this webinar. A quick reminder that our second webinar will be held on June 24th, given by Professor Kit Wang from University College London. You can also go to our webinar website for more information. Okay, so looking forward to see you all in June 24, and thank you, Professor Liu and all, and wish you a great day ahead.
Thank you, everyone. Thank you, Nina, for chairing such a great section. Thank you, everyone.
I hope we can meet in person very soon.
Yeah. Look forward to meeting you in person soon. Okay, yeah. Thank you, everyone.
Okay, bye-bye.
Bye-bye.
Bye-bye, 世博.
Bye-bye. Take care.
Bye bye,
Take
Lina.
care.